in the chat.
Yeah, and if you have any questions at all, just ask them as during the presentation. Yes, I'm just going to talk a bit about your background to physics modeling, a bit of a background on the laser rate model, which is the one that was in the Python notebook, some context on it, then just discuss the solutions to the questions, and then maybe discuss the time-based solutions if you've any questions on that. I've put this presentation is in the chat, and the solution to the time-based problem is in there as well, so you can download those. Physics modeling, yeah, I suppose a good way to think about it, or something I found useful, was I used to hear people say, oh, that's a model and that's not a simulation. So I always thought they were kind of the same thing to begin with, but kind of thinking about it more like a model is more, it's generally more simple, where you might just be looking at one parameter at a time. Generally in a model, you'll understand everything that's happening in it, or, you kind of want to understand everything that's happening in it, and it's quite a bit more simple, whereas the simulations tend to be bigger. They'll be modeling many different parameters all at once. You'll be more focused in finding out the answer at the end, and the answer at the end being correct. Whereas in a model, you kind of more want to see what's happening at each step in the model. A model is kind of more for understanding, whereas a simulation is for the result. So reasons why you might want to model or simulate. I mean, it's more than likely it'll be cheaper than actually making a semiconductor device. That's not always the case, because modeling software can be phenomenally expensive. So modeling software can be 100,000 euros a year just for a license. Modeling can often be faster, but you have to kind of be good and know the software first. So, if you just want to buy software to model something, you'd have to allow a lot of time to kind of get comfortable with the software before you could come up with good models. Yeah, models and simulations can be inaccurate. They're often based on approximations, but they're faster. That's generally why you would do them. And generally they're cheaper as well. So yeah, simulation will tend to be done more in commercial software. You don't have to think about what actually is happening in terms of the maths in the model. You just know it works, and you put in the parameters and you get the results. So modeling and simulation can be really accurate for certain areas. So RF electronics, or electronics in general, and optics, so modeling lenses, you can almost design a product in that software and you can be fairly sure the product will work. Whereas something like a laser model, because there's many different things happening, it'll be less accurate. You'd be less sure the result is right. Yeah, so reasons for modeling instead of simulating. So modeling, you tend to be looking more at the theory of what's happening as opposed to the results. Modeling is more likely to be done on homemade software. So something like I sent you, that would be more like a model, because you know what's happening in each step. Yeah, and one of the things I found is things you can change in the simulation or model can actually be more accurate or have more resolution than in what you can measure in an experiment. So one thing I'm looking at the moment is changing things in a laser cavity, and I can move these features by a nanometer, and I can see what effect that has. Whereas in an experiment, you couldn't do that. Your resolution might be a micrometer. So it does have that advantage as well. As computers become more powerful, simulations become more significant because they become more accurate. So you could just learn a piece of simulation software like HFSS is one of them for RF, or there's also ZMax for optics, and you can just have a career by knowing that software, and that's all you'd have to worry about. And the thing is, you don't even really have to understand what's happening. You just have to know how to use the software. I don't know if that's good or bad, but that's kind of where modeling is. Yeah, modeling will tend to be more towards academia because you're looking more at the theory, and often you find modeling software or simulation software will have started as modeling software in a research group, and then over time the research group will perfect the software. They'll start a company, they'll start to sell the software. So software often moves from modeling to simulation. Yeah, physics modeling. So I wanted to give the analogy of the Zeno's paradox. So it's the idea in if you have an engineer and you have a mathematician, Zeno's paradox is if you were a meter away from a line and you started walking towards this, and if you halved your step, each step you took, you would never actually reach that line. Which is correct in maths, you wouldn't ever reach the line, but in engineering, you could just approximate that eventually you can't make your step any smaller, so you'd have to step over the line. So I suppose what I'm trying to get at is these models aren't completely correct, but they are correct enough to give a right answer or an answer you'd be confident in. Yeah, so physics model is about making good approximations, and understanding the approximations is what's very important. Yeah, when you're making modeling software, it is important to make the software as simple as you can. When I first started doing it, I added in all different kinds of parameters, and you'll kind of find that you've written the software and you think it works, but there'll be something wrong in it, or a few things wrong in it that you can't pick up like you would pick up in regular software. And it'll be after like a couple of months of using it or something like that, you might realize, oh, that parameter should have been something else. So really, physics modeling instead of normal software writing it's about making the software as simple as possible and understanding everything in it. Yeah, only include what's necessary and leave out parameters that will have like a small effect or a predictable effect. So something like temperature might have a predictable effect, so you might include that. Now, in some cases, temperature can have a huge effect, so you might want to include it. Or something like dispersion, dispersion in optics. Yeah, test. So if you write software, the most important thing you can do is keep testing it against if you have actual devices, or you can test your software to see if it makes sense, if the results it gives are something that's physically possible. So what's next? Yeah. So if you want to get into physics modeling, you've kind of two routes. You could learn a commercial software, like I mentioned, or you could learn a code. I suppose to start, the best thing to do would be to try and learn a code. So there's many different options. All have their ups and downsides, except for there's this one Julia, which is quite new software. I think the only thing it would have against it is it's quite new, but it seems to overcome a lot of the problems that something like Python and C would have. So Python is really easy to code in, but it's really slow because it has to interact with your operating system all the time. Whereas C interacts directly with your computer hardware, so it's a lot faster, but it's really hard to program in. And then Julia, the whole idea is it combines those two, so it's easy to code in, but it also interacts directly with the hardware, so it's supposed to be the best. But I haven't done it myself yet, so yeah, keep that in mind. Yeah, parallel computing is quite important. So parallel computing, there's different kind of codes in it. So OpenCL is quite like C, but it's more for specifically talking to your processor or your graphics card. So the graphics card is the big one because your graphics card will have a lot of kind of really simple CPUs, which are useful for physics modeling, because you can carry out 10 times the amount of calculations than your CPU could do. But again, it's hard to program on your GPU. Hardware, if you're starting off, it's best to start off with Intel hardware and NVIDIA hardware as opposed to AMD and I can't remember the other companies because they're much better supported. Um, if you want to, learn a different operating system, if you're working with software, commercial software, Linux is or Windows is better because it's more supported. But if you're writing your own software, I think it's a lot easier to write on Linux. Like a lot easier. It's almost worth like learning a new operating system to do it. Yeah, so it's worth starting with bare scripts, to really learn a language. But then when you get used to it, it can be worth using an IDE because it'll show you how to write a language properly. And writing code that's readable is also very important because you can leave a group or a company, and the next person that comes in has to be able to understand what you've written. So that's important to keep in mind. Finally, right, the laser rate equation. So this is what I had sent you around in that notebook. It's one of the most used. It is probably the most used model in photonics. It's a very good example of applying a model to a situation. So the model I've given you, it outputs what's called this light current curve, or what's known as an LI curve. So the sweep it shows is you're increasing the current on your x-axis, and the y-axis is your power output. So it indicates, first of all, if your laser is working, second of all, how efficient your laser is, third of all, well, I suppose they're the main ones, it's working and it's efficient. Yeah, so it indicates the threshold current, the slope efficiency, and output power. So these are really important design targets for a laser. The first thing you do almost with a laser is you would design what you want its threshold current to be, and well, maybe its power output first, and then you would design what you want its threshold current to be. There's many different reasons for this. So you might want a higher power device with a higher threshold, or you could want a lower one with a lower threshold. But it'll be design. You're almost like first design targets. Yeah, so it does these LI sweeps. If you're doing it, it'll show you if your laser is working, if the fabrication went okay, and then also the model. So the whole idea of the model is you can change a certain parameter like the reflectivity of your facet, and you can see what effect that will have on the rest of the performance of the laser. So you might want to increase the reflectivity of one of your facets to get more power. To get more power at the other end of the laser, and then you can see what effect that will have before you actually go and make the laser. So you get an idea of what it'll do. Yeah, so the rate equations, I haven't done a full background read on it, but like rate equation modeling seems to have kind of first come up in chemistry. So you'd add a reagent, or you'd add two chemicals together in a beaker, and it would tell you how fast the reaction would happen. And, it seemed to work well in that scenario. And then in a laser, you've got photons and you have carriers, electrons and holes, and it's not exactly, but it's a fairly similar process. So if you know the model works in one situation, you can apply it to another similar situation and get good results from it. Yeah, there's other factors. Then your laser isn't exactly two chemicals coming together like in a beaker. So you do have this kind of overarching E field that drives the stimulated emission, which you can add factors then to account for that. So that would make your rate equation model more like an actual laser by adding in factors. Yeah, so we've just looked at a steady state version of it. You can also do the time-based one, which I sent around as well. The steady state one, we have to make more approximations to keep it a simple model. Yeah, so I can show you what I did, and we can talk about that then. Okay. So the first question in there was deriving the steady state from the two rate equations. I mean, these questions, they're not. I just put in these questions to get you to think more about the subject. They're not kind of foolproof questions. So if you found the questions frustrating, it was only just to get you to think about the material more. But anyway, so um, yeah, we were trying to derive the steady state from the two rate equations. So obviously, the first thing you do is in a rate equation in the steady state, you've no change. So you set both the dn dt and ds dt equal to zero, and you get these two equations. Now, the next step I don't really understand myself, because I don't think it necessarily has a mathematical reason to do it. But if you know the result you want to get, it kind of makes more sense to do this. You add the two equations, and that cancels your gain factor in each one. Um, and then it leaves you with these four factors combined. Yeah, so then the four factors all combine together, and then what you want to do is your current is your input, so you want to put that at one side, and then everything else is going to be your output. In this case, we're going to switch it around at the end. Yeah, so the main approximation we're making here is we're holding the current, because actually, I mean, this is what I say when I talk about approximations. This isn't closed, this equation. So if you change s, you're automatically going to change n as well, which leads us back up to here. But we don't want to go back up to here because this is more difficult to solve. So we have to make an approximation to keep it easy to work with. So what we do is at threshold, we know well we know that at threshold your carrier density is effectively clamped or quite close to being clamped. So what we do is we put the carrier density at threshold into the equation, so we don't have to worry about n changing, and then we get an equation we can solve, a linear equation. So yeah, it's important to understand that application of an approximation. So then we get this equation, and actually S is what we want, the photon concentration. So we put S as our output, and then this all becomes our input for the calculation. Yeah, question 2. Question 2 was kind of based on this. I'll call it an approximation. It probably isn't really an approximation. I kind of only did it for aesthetics more than anything else, because the approximation we have made with our new equation, this will only hold above threshold, the threshold current, this knee point here, and doesn't describe what happens below threshold. So I didn't want you guys to run this code and then to start getting these negative power values, because it wouldn't have made sense. But that's a good way to test the model. If you put numbers in and they don't give you a physical answer, it gives you an idea that your model is right or wrong, or yeah, it kind of gives you an idea if your model is right or wrong, or the range your model will hold in. So this model won't hold over all values of current, and it'll only hold over values of current greater than the threshold. Yeah, so that was a bit of a sneaky question, but I just wanted to get you to think more about the model. And yeah, this was the this question was just input the values and then see what results you get. So this is kind of the application of a model. There's one or two kind of sneaky things in there. The first one was you have to remove the quantum well numbers here. I had the quantum well numbers pegged to the confinement, so you have to take quantum well number out of it. And we see for our first one we want 15% confinement, so we put in 15%. We want our mirror reflectivity is 0.5, so we put that in. It is 0.5 already, and then our cavity loss we want to set that to 5. And then we run our code, and then this is the LI we get. So I can't read that exactly, but I've done this calculation before, so I know it's 10.7. And then our maximum output power. Oh, sorry, we had to increase the range as well. I did set it to 150, so it's you had to notice that that should have been increased also. Yeah, so there we go. So we know the threshold current and the output power, and then slope efficiency. It's an important parameter in lasers. All you do is you take your threshold current, and then you take the current at your maximum output power, and you see how much your power changes in that band. So you get literally like a slope, a positive gradient. And then you just divide one by the other, and it gives you an idea of how well your laser is working. I didn't think these questions out enough, so we pretty much got 0.25% efficiency for each one. But yeah, that's how you do that anyway. Yeah, so after that, they are mostly the same. You just change the parameters. So I'll take this number 4 here and put in 7. And we'll put in 0.3. And then we put in 300. Oh, sorry. Okay. Anyway, we put in 300. And we will put in 10%. And yeah, okay, reload that. Again, this is our LI that was output. So we know the threshold current, we can read it from the graph, or you can print it in Python as well. It's 13, maximum output power is 34. Again, a slope efficiency of 25%. The last part did have a kind of a sneaky part in there again. So I changed the reflectivity of both facets, and the tricky part here was just to know how to change those. So what you had to do is, instead of having 0.3 squared, you had to do 0.2 times 0.8, because it's squared when both your reflectivities are the same, but when they're different, you just need to multiply the two reflectivities. 7 is correct. 0.8, and we put in 700, and we're still 10% confinement. Yeah, and we get our output results: 19.7 threshold current, 32 milliwatts output power. And again, unfortunately, the same efficiency of 0.25. Yeah, the time-based calculation. I mean, this is kind of what you should get from it. Eventually, you should get these two graphs. This top graph, this one in blue, is describing your carriers, so your holes and electrons that are in the cavity and how much they change with time. And then the second one is how much it's optical power, but it's also photon concentration or photon number in the cavity, and how much that changes with time. So basically, what this steady state one, effectively what we're doing in the steady state one is, we, instead of doing all these calculations, we just go to where the calculation is in the steady state, and we read off the power here. So that's, if you can kind of imagine, this LI curve is just this steady state version of this optical output power with time calculation. So the reason I didn't do this is this is another kind of relevant example, is this calculation takes quite a long time to do on your computer. It'll take maybe 5-10 minutes or something like that. So it wouldn't be reasonable to do it during a presentation like this. So that was one of the reasons why I went to a steady state. So you kind of have to keep in mind your available kind of computing power when you come up with these models, and particularly how much resolution you go into in the calculation. Well, I think I've said everything I can say really on that. Any questions? I'd be more than happy to answer them.